So thank you, everybody. It's great to be here. And yeah, I hope it will be an enjoyable talk at the end of the sessions. So the topic is anomaly detection, root cause analysis, and explainability and how they connect. So I hope some of you have seen the enjoyable talk before that in the other session about art. And in our case, the picture I'm looking at are not so exciting. These are time series. However, the time series contain a lot of information with a lot of value for us. So time series are data points which have a natural ordering in time. Usually they describe evolution in time of a system where we have several sensors measuring the evolution of it. And they correspond to something like a beating heart of the industry. And we have to understand and analyze them. The next topic I'm speaking about is anomaly detection. So what are anomalies and why do we care? So these are patterns in data not conforming to expected behavior. So you can see on the left the time series most of you know about. These are actually, it's electrocardiogram, which you get if you go to the doctor to check your heart. You can see the pattern with your eye in blue, and this is the pattern you expect. And then you see something in red there. It's a pattern which is not expected, and it corresponds to a real medical condition. So we care about anomalies because usually, once we detect them, it will be translated into actionable insight, which will generate value. In this case, you detect a medical disease or a condition, and if you take care of it, you generate a tremendous value for the human because, well, health is the most important thing for us. On the right-hand side, you see a similar example from an actual subsystem of an airplane, maybe, where you see, if you focus on the red curve, you see an area where there is an oscillation, and there is a red region drawn around it. So this oscillation is not expected there. It's not bad, it's not a critical condition, let's say, but still it's something unexpected. It might correspond to an oscillation in a valve. So the valve opens and closes, everything works perfectly. However, these valves are designed for a particular number of opening and closing for a lifetime. And if they do it without purpose on themselves, the lifetime gets reduced. So they break earlier than expected. This causes money, so you have to replace it. You have to replace this in a place and time which you are not, you don't want to do it. So this creates problems which we want to solve. So essentially, we want to have the ability to detect unwanted or behavior early on. And by detecting it early on with an early onset, we of course can tell people that, wait a second, now you have maybe a couple of weeks time to do something about it, and do it in the time period where it's best for you. So if you're in a period where you can do something about it such that it's not generating added costs. And this is called usually predictive maintenance. So people are not maintaining in regular intervals and not when something is broken, but anticipating it. Very important for, obviously, for many, many use cases in manufacturing, in systems, and so on. Okay, so how do you detect anomalies? If you take up a regular book, well, first of all, you have to define what is normal, and by definition, then everything which is outside of this region is anomaly. So it's simple. So you find features describing your system, and if you find the right one, it looks like the plot on the right. You have two features. Each point corresponds to a system state, and you see in most cases, there are these two big regions where the system is in, and then there are some points outside, and just by looking at it or creating very simple kind of decision boundaries, you can find, well, these are my anomalies. Very easy. Why it's a difficult topic? Because if you do it in real world, and these are real world examples, the pictures look like this. It's very hard for me and for my signal processing, my brain, to detect anything in the picture above and as well in the picture below. So this, obviously, the feature which have been selected by some algorithms are not right. So defining what a normal region, which encompasses every possible normal behavior, is very difficult. There are different modes of normality. So the usual methods may lead to confusing results. And also, sometimes you detect something which is clearly outside of the regular scope, but it's just noise. So there is no insight generated from it, and you cannot generate value. So how to distinguish between noise and essential anomaly is also an open question. And so we are developing several different tools to be able to do better than the pictures here. So what is the, let's say, standard approach in the field to do it? You do use deep learning. Usually you use something like autoencoders. So what it means is that you need to learn what is normal. In order to do so, you create a model and train it on huge amounts of data or large amounts of data. And by definition, anomalies are rare. So the most part of your data will be normal. And the task of the model is to take your input time series in many dimensions, compress them somehow, and then recreate them back. So it learns on this huge amounts of data. So if you give it a normal time series, like in the picture on the left from the top, it compresses it and reconstructs it back without any problem. Then, in operation, it encounters a time series which was not represented or very seldom represented in training data. It goes inside, it compresses it and tries to recreate back and fails. So there is a clear difference between the input and output. Maybe sometimes the difference is very small, slightly, but still significant enough. And so you quantify this as a deviation, and it's a first indication that something gets wrong. So this might be an anomaly. Well, great. And so we have now some anomaly candidates, and so who is making decision? In our case, the final decisions are made by engineers. So the engineers have to take these anomalies and then have to act upon them, replace parts, say that something has to be done, maybe stop production machines. And so the decisions might be costly if they are wrong. And so in order to create a model which is being used in production, we need to generate trust in our predictions. And it's very hard for unintuitive, let's say, time series, which are not nice pictures, to generate trust. How can we do it? Well, first of all, you can have a kind of completely black box model where you just prove mathematically that it covers all of the possible kind of input space, and then you have to trust this blindly. So it's always right, essentially. Well, engineers are first not take it, so like mechanical and systems engineers, they don't like it if you give them a system and say trust it, even if it's against your kind of common sense. And also, you cannot make these guarantees. So you need to generate trust from interpretability. They have to understand why the system has made this decision, when it can go wrong, and why it makes a wrong decision if it makes one. And by understanding when it happens to be wrong, it generates trust in the other cases. And also we can use this understanding and their reports to improve our system. So we need some kind of interpretability or traceability in our models in order to generate trust and generate value later on. So on the right, you see two examples of false positives. In both cases, these are false positives. They normally should be in the orange sensor. In both cases, there is no anomaly in the orange sensor. However, in the case above, there is a connected sensor in green, which goes completely crazy. So something is wrong in a connected sensor, which is describing the same subsystem. And our model picked it up and translated it into some weird behavior predicted for the sensor, which was not anomalous. So while this is a false positive, it actually has value for us. However, on the picture below, we have a case where we don't know why our system failed. There is no reason for it as far as we could understand or engineers can understand. And so we are coming to the topic of explainability. So now we have to connect anomaly detection with explainability. So what is explainability? Essentially, there are many definitions on the market. So if you read papers, you can find different statements. So one of them is that explainability is essentially something on the user side. The user has to have the ability to understand systems logic. And the property of the system itself then should be interpretable. So either it's some kind of so simple so that it's self-interpretable, like linear regression model. If you look at it and you understand a little bit of math, well, you can see how each weights contribute. Or if your model is kind of a black box, you need to provide something on top of it. Something which takes its input and decisions and gives you a simpler kind of a proxy explanation for it. Like in case of computer vision, there are many examples on the market, like the example on the right. So why has the system decided this is a dog? Well, you can see that there are some regions in the input space, like the facial figures of the dog, which led to the decision. Essentially, they were important. At least you can see that, well, it's connected. The decision was connected to the dog and not to some background noise or something, so it's kind of okay. The challenge for us is firstly that our models are usually black box, so they are not self-interpretable. And second, there are no or very little systems which provide explainability for time series. It's in their infancy. And so, in the end, since we cannot provide explainability so easily, the generation of value from this kind of anomalies, if they are not very severe, is also in the infancy as well, and is challenging. The final topic which connects with it is actually the third step. So imagine you can understand that you can detect a disease, you can check for disease risk and maybe warn the patient that the heart condition might evolve, so please go to the doctor or take medication against it. But maybe you understand also the reason why the condition arose. And if the reason is not only age, which you cannot change, but really something else, you can do something about it. So in case of heart diseases, maybe you should do more sports in the first place so that you don't get it. In our case, the root causes are much more complex. But if we find them, we might prevent the occurrence of anomaly in the first place for many examples. So this is our, let's say, next goal and something we do in parallel with anomaly detection. So the field is called root cause analysis. And here you can imagine that there are symptoms like branches on a tree in the outside world, what you see. But they are fed by something deeper, by some deeper connections under the ground, the roots of this tree, the root causes. And these are usually called root causes if they are the most basic causes that can reasonably be identified and that management or us has control to fix. So it's not valuable to define a cause where you have no control about because you cannot do anything. It's better to find something way up where which you still can fix. So imagine you are airline or airport operator and you have a low tire pressure in your plane. This is a symptom. There is an intermediate effect. So you can detect that there is a hole in the tire. That's why the pressure sensor fell down. But the root cause was the damaged runway in the airport. And so you need to change the runway in order to prevent the occurrence of low tire pressures in your planes later on. And this is something which you has to detect. So this is interesting, and we applied it with different methods, data-driven or not data-driven, in many different areas. Here's one example for a non-real-time. So here we are speaking about non-real-time methods. So we gather the data, anomaly is detected, and then we do try to understand what's happening. A data-driven method where we could use it without having the domain and expertise about the system itself. So this is connected to an Airbus approach which was patented. And the idea is simple. So first we need to detect the unwanted events. So we need a couple of samples of anomalies. We need a couple of symptoms to find. And then, in order to ensure something which is connected to causality, it still can be correlation, but at least we look for windows in other sensors which might be explanatory in windows prior to the occurrence of events. So the cause should be prior to the event itself. So we have some causal connection there. And we compare the behavior of the sensors in windows prior to the event to their behavior in windows somewhere else in time series, which is also not so easy. But you can do this comparison and then you use standard statistical tools, p-values, whatever, compare the behavior, and you might find interesting results. So the plot on the right is called Vulcan plot. It's used also in medicine. You can see on the x-axis the strength of association between variable and event. And on the y-axis is statistical significance. So higher is more significant. And you would expect that there is a kind of rise to both sizes. So if it's very negative strength of association or very positive, usually the significance should rise as well. It's more prominent. But sometimes you have maybe not enough data, so it might be still a kind of fluctuation. And then now you have, and each point is a system variable. It's behavior of a system variable prior to problem and in other areas. And you see here that now in the topmost regions, so high statistical significance and high strength of association, now you have a subsection of variables which behave differently before an anomaly occurred from their other behavior. And now you need also to reduce the space and provide kind of more explainable connection. Here we use machine learning on top of statistical methods to take their explainability for some simple models into account. So for example, we use random forest, which provide some measures of feature importance. So we use only the features which were important in statistical methods. Then we train a surrogate model, which should be able, from their behavior, to predict that the anomaly will occur. And then we look at feature importance and select the most important feature as root cause candidates. So now we have a lot of features, then we subselected some of them which have statistical properties which we are looking into. Now we use machine learning as well on top. And then we use, for example, the partial dependence plot. What does it mean? We now take only the most, for example, the two most significant features, and then we vary only them and keep everything else the same. And now you can compute the probability of event given the behavior of these two features. So you see here one feature on the right and the other on the vertical. So for small values of this one feature and very high values of the other one, the probability that the event occurs rises to 90%. So obviously this region, so if these conditions occur, one variable very small, the other very high, anomaly will happen. So the combination of these values of these features is identified as a root cause. Because you clearly have in statistical sense, if these two conditions occur, you will have an anomaly. So this is very interesting. And of course, this is only the beginning. And especially for critical systems. So if you think about systems which are not on ground analyzing data afterwards, but systems which might be embedded inside an airplane and we want to fly with it, we need to be much more on so we need really to trust the system and understand them. And so there is a big project in France, the DEAL project, about dependable, certifiable, and explainable AI, where a lot of French institutes are working, as well as Airbus and many French companies. And there is also a library which is open sourced, which you could look at, which combines many of the, let's say, feature attribution and visualization techniques for explainability. Still, if you look for time series, it says something in work. So the time series are something which we have to go into more detail ourselves, which is very interesting, and it's an interesting part of the work. So I was trying to show you here that there is a deep connection between anomaly detection tasks, root cause analysis tasks, and explainability, which can be used in both cases, not for the sake of just to explain something, but in order to generate actually value from it, because the most critical decisions are taken by humans and they need trust into the models. And we need this understanding of the models in order to improve them in this very unintuitive space. And because for the root cause analysis to make it data-driven, we need also explainability techniques. So we have a couple of in-house libraries which we use for this, specifically tailored for our data types. And we have now a master thesis specifically on explainability in time series. And I'm very curious myself to see what comes out of it. So thank you very much for your attention.